Just testing my setup over here, making sure everything's ready. Hello? No. Okay, cool. Just testing my setup over here, making sure everything's ready. Hello? No. Okay, cool. Just testing my setup over here, making sure everything's ready. Hello? No. Okay. We've got 10 minutes and then we can kind of start this thing out. I'm just gonna share the links and say the people and make it that it's ready everywhere. Um, uh, making sure that it's ready. Mm, 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 mm. Yeah. Hey guys. Yeah, so let me see. Okay, check. So we have the stream running. We have um this thing sometimes is a problem. I'm gonna fix it now so that we have good clear audio. Like that. I think that should fix it. Make it so my audio is good. I'm just gonna go on YouTube and test it. Mm, mm, cool. I'm just gonna go on YouTube and test it. Mm, mm, cool. I'm just gonna go on YouTube and test it. Mm, cool. Works. That works. I'm gonna start a dockable window, docs, YouTube chat, I think. Yep, so that I can have YouTube chat and I can say we are live. Got in. Perfect. We're live. Okay, cool. So just passing some time so that we can get to our time then, and then we can start the stream. I'm gonna do a last few announcements now. Make sure my streams are being shared, and then I think that is it. We can go. We can go. We can go. Oh, we need stuff for that. Cool. So that here. I need to go on YouTube. Be live. Get the live link. What's this? Share. Copy. Cool. On now. Now. Yeah. I need to share that link a few places. Streaming. Accelerometer. Driver. There. It's there. Okay. Perfect. 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 And the links. Link it on. Now. Now live. Cool. Perfect. Okay. It's 9 in the morning. Everything's set up. I have streaming set up. I have streaming working, and we have our objective.
So what I'm going to do today is I want to interface, not interface really. What I want to do today is I want to collect some data from an accelerometer, and I have a few. I have a few around. So I do have. I think no, that's a logic converter. But give me a moment. Give me a moment. Do give me a moment. I can find out what I need. I'm just looking at the sensors I do have. Basically, what I do know, I'll just pick this as I find out what I'm looking for. I do have some MPU 6050 accelerometers around. It's cool to go through your box sometimes because you find stuff that you didn't know about. Yeah. In any case, it's too small of a board to see, and even if I found it, I just found a time of flight laser and all of that. Cool. In any case, it's too small to see. I really want to show this, so I'm gonna go find it, and I'm gonna go find it, bring it, show it, and then we can go on with something else. Okay, cool. So, because I want to show it. I'm going through my lab. Okay. Not in there, definitely. Time of flight. The processes. Those are real-time clocks. Real-time clocks. An expander board. Just pardon me. I'm gonna find it just now. It's somewhere here in my box. And it's a old project. This. These in here. And some small parts in here. Real-time clock. Caps. Strings. I think that's a logic level converter. It's so funny because one day you find all your sensors and then some days you don't find any of your sensors and you're like wondering where they are. And they're always all right in front of you, quite close to you. Yeah, found it, see? It was like exactly where I wanted it to be, but not where it was. But basically I have this little guy here, and this is I'll just open it so we can see. So this is what is this? I hope I'm not wrong. I hope I'm not misleading you guys. Yeah, so it's gonna be really hard to see. But this little guy, if you can just focus. If you squint really hard, you can see that's an MPU 6050. And an MPU 6050 is is 3-axis how do I say it? 3-axis accelerometer. And basically MPU 6050, it's just a triple axis accelerometer, which means it's an accelerometer with like X, Y, and Z axes to read from. Now, today we're going to be working with the LIS3DSH. I don't know how to say the sequences, but we're going to be working with the LIS3DSH, which is the onboard accelerometer that you find on your STM32F407 Discovery 1 board. So that's this guy. Comes with an SD link. Comes with quite a few number of peripherals that you can use for quite a few number of things. You have GPIO, you have I2C, you have SPI, you have UART, you have USART, you have CAN, you have ADC, BAC timers. You have an I2S peripheral. I think you have some parallel. I don't think this one comes with LTDC, but in any case, so one of the discovery sensors that we have on this board is actually an onboard triple axis accelerometer. And what I want to do today is I want to access the accelerometer on this board and read out data from it. This is going to be some sort of build up into uh, using DSP on your microcontroller and how you would use it, why you would use it. But for the first part of this, we need to do is we need to go into we need to find out how the microcontroller works, and then we need to also find out where this peripheral is connected. And then once we find out all of this data, we can go about now communicating with the peripheral and kind of doing stuff with it. So I think the first thing is to look at the data sheet of our board. So our board's data sheet. If we look at our board's data sheet, we can find out what the peripheral is connected to. I misspoke. Schematic. Or what is this document called? This is it's a user. It's the user schematic for the board that we're using, which at the moment is the STM32F407 Discovery one. What we need to find out is the MEMS accelerometer. So in this document, I'm just going to do MEMS. Perfect. There's a few more MEMS things. It's just not it's not only the accelerometer. MEMS is a package, which is something like microelectronic. We'll look at it just now. But what we can't see here is that this accelerometer is actually connected to, let's see. So, okay, cool. I'm supposed to be here. Okay, so now we can see. Sorry, I just got confused there. I was zooming and it was zooming on my desktop rather than on my PDF document. So what can we see here? We have an LS3DSH MEMS accelerometer, and this accelerometer is connected to SPI1. SPI1 with the clock being on 5, master out, slave in on 7, master in, slave out on 6, and we have NSS or chip select pin on PE3. So the first step here would be for our board, which I've already pre-done because I wouldn't want to do that that's not like the objective of today, is to get SPI1 working. And we need to get SPI1 working so that we can do the things that we just discovered in come on, that document. So sorry about that. Sorry, I closed it. That document. So we need to connect to SPI1 because this peripheral is on SPI1, and then so we need to activate SPI1 and then use PE3 as the chip selector. So let's just look at a summary way of doing this, of initializing SPI1, And then after we get to that, we can now look at getting our own little peripheral that is on, I mean, our own little sensor that is on SPI1 working. Okay, cool. So in case anyone has any questions, please feel free to send them out on the chat. If you send it out on Discord or in LinkedIn, I can only answer them after the live stream, but that's okay. Cool. So what I went and I did is I have a blank CMSIS project. There's links to blank CMSIS projects of this sort. I can show you. So if you want the beginning of this project so that you can kind of follow along or do anything with it. So I have a blank project here that probably does something like put on an LED just to make sure it's working. Yeah, it toggles an LED to make sure it's working. But as you can see here, my link is blank F4 CMSIS, which is on GitHub or under my user Zach. Okay, so this is my starting point. This is the project that I'm going to use. This is my initial point of my initial code is going to look like this. So after that, what I went ahead and did was I did a quick SPI driver. I just initialized SPI. So let's look at it. I have a SPI driver here that's quite basic. If you've watched any of my videos, you already know this SPI drivers if you've seen my SPI driver development videos from before. So what we do here is we have some functionality to initialize SPI. We need functionality to deinitialize SPI. We have SPI clock control. We can send and receive data using SPI. Then we have some functionality to clear the overrun flag, close transmission, close reception, SSOE, and such. These are all just convenience functions, basically. You can have SPI, you can run SPI, you can initialize SPI, you can deinitialize SPI, and you can send data through SPI. So what we're doing here is we're using non-blocking. Basically, this is interrupt-driven data communication. What does this mean? Whenever we do send data, we use interrupts. So our send data doesn't really look like send data because from what you can read here, we just enable an interrupt and then things happen from there. And it's the same for receive data. We enable an interrupt and then we have this basically internal callback functions. Can I say them? The application uses this callbacks to handle TX and RX of data. How does the application do this? So let's see. So one would go about and do something like, okay, let's go to main. We have SPI init. Go to definition. And what you can see here is I initialize the MOSI, the MISO, I initialize the clock, and then I initialize the chip select. And then once I do that, I enable my SPI with the bus configuration that we want for the device that we're talking to. In this particular instance, we're on SPI1 and we're going to be speaking to this accelerometer, and it needs us to be talking in 8 bits. The polarity is low, the phasing is low, and we will enable software slave management so that we can control PE3 by itself to select this chip. So because this chip is always connected, it's on the board. So we're using, and you might want to use SPI1 with something else. So we use P3, which is not connected to SPI1. It's just a general GPIO pin, and we use this pin when we drive this pin low, it selects the peripheral. If we drive this pin low and SPI1 is activated, basically what happens is the peripheral on SPI1, which is our MEMS accelerometer, becomes selected and we start communicating with it. One minor caveat I might want to mention, really, the thing I would want to touch on is SPI1 on STM32F4 is tricky to get enabled. So what you need to do in order to enable SPI1 on the STM32F4 is you would need to disable I2S. Okay, you need to disable I2S. Basically, you need to point SPI1. The peripheral SPI1 is shared with an I2S peripheral that I think is the default that's the one on. So you need to disable the I2S peripheral for SPI1 to work. This is not a case for SPI2 and 3 and 4 if you have other variants of the F4. So this is kind of the thing I would note. Just remember that you do need to disable I2S for SPI1 to work on the STM32F407. Cool. That should be kind of what we need to cover for SPI. I mean, the other parts of this is just that it's a normal SPI driver, okay? And when we use it like a normal SPI driver. So basically, at which point are we in right now, which is 20 minutes into the stream? We have code that will operate an SPI peripheral for us, and we have the pins set up so that we can actually use SPI1 on the 32F407, STM32F407. So what we need to do now is to go through the documentation we have, find out how to speak to this peripheral or to speak through this peripheral to the sensor that is connected to this peripheral. So there's a peripheral, SPI, and then there's a sensor, the MEMS accelerometer. We need to use SPI to speak to that MEMS accelerometer. We now have working SPI. So what we need to plug in is code that uses the SPI driver we built to speak to the MEMS accelerometer that's on here. So let's look at some code. Let's look at them. So before we look at some code, so the way you do drivers of this sort is you would want to depend on quite a few documents. Okay, so number one, you need the data sheet. Is it a data sheet? Yeah, I would call it a data sheet. So you need the data sheet for the accelerometer that you're using. And today, or rather, whichever sensor that you're using. And today since we're using the LIS3DSH, I'm just using the ST link. I'll paste this. I'll put all these links in the. I will put all these links in the description. So I'll just go on my channel and I think it's probably Studio. What I'm saying is I will put all these links in the description of this live stream, and you should be able to. Okay, cool. Just a moment. Let's edit that here. Okay, cool. So links. LS3D LS3DSH data sheet. Okay, so I'll add this data sheet to the link to the, how do I say? I will add this data sheet to the live stream, and then I will add LIS3DSH app note. I'll also add the application note because this is gonna this the other document tells you about the device. This tells you about how to use the device. And then the other thing I will add as well is GitHub Zach UC DSP. Okay. Repo, GitHub, repo. Okay, cool. So don't be too safe. Okay, those two links are in. Those three links are in at the moment, and you can follow along with them. But I'll just, for the rest of the links, I'll just keep a note of what links I need to add. Okay, so what was I discovered? So you need a number of documents to help you actually come up with the driver for the sensor that you want to come up with. Number one, you're going to need a datasheet. The datasheet by itself could be sufficient if you're experienced enough to build up the driver. It is quite a large document, and it speaks in very technical terms, and so you would have to read it. It's almost you almost don't read it like prose. You read it like you read. In my experience, I found that the I read the data sheet in, you almost read it like a program. You go into the main function, then you jump into another function, then you jump. So you're kind of going from chapter to chapter to chapter. So like in this instant, what I would want to find out, number one, is I would go on the table of contents, and then I would want to find out about SPI serial communication. Cool. So number one, I can see here that in order to enable this, in order to select this device, it wants the chip select signal to be pulled low. Okay, cool. So number one, we know chip select needs to be pulled low in order to select this device. Cool. So let's we'll put that down. Okay. And then serial SPC. What is SPC? SPC is serial SPI clock cycle. Okay, so this SPI clock cycle looks like it's how do I explain this? The rising edge. So data is sampled on the rising edge, which means this is gonna be a polarity of, we've already set it up here in our main. So you can see all these settings now you can see how we're using. So we have a polarity of low. The clock polarity is low. So what that means is we're going to the clock is going to start from low, and then it's going to go high, and then when that transition happens, we're going to have samples of data. Data is going to be sampled. Cool. What's the other setting we want to know? So we want to know how many bits are moved at a time. So we want to know how many bits are moved at a time. So this is probably I'm going to read CS whole time, input time. This is all just timing data. And I want to go back. You see, so I basically am just demonstrating this. You want to jump back to the table of contents, and then we want to go back to and find some sort of instructions on how to operate. SPI bus interface, read. So okay, cool. Let's look at that. So this should tell us a lot. CS is a serial port. It enables control. It goes low at the start of the transmission. So, like I said, it needs to go low for the thing to start. Cool. SDO and SDI are basically the MOSI and MISO. Okay. SPC is a serial clock and it is controlled by the CS. It is stopped. It is stopped high when CS is high, no transmission. So it goes high when CS is high. So this clock is inactive when it's high and when CS is high. Okay. So, and this is how we send the data. So the 0th bit is our read or write. Bit 1 to 7 is the address we want to read or write. And then bit 8 forwards is usually the data coming back from the sensor. So, and I think for today, we're going just to do like single bit reads and just to get the accelerometer data. And once we get that, I mean, later along the line, we can make it so that it reads multiple bits, but at the moment, we just want to get the thing working. So we have most of the settings that we're using here. So we know it's low, that's fine. When we enable, then let's look at something. Let's find out which data. Okay, cool. This is the data that is written into the device, MSB first. This is the data that is read from the device, MSB first. What have we discovered? Most significant bit first. So in our SPI driver, we need to make sure our SPI driver does you enable most significant bit first. Okay, cool. So we've enabled that. So we're finding out. So far we know how to enable this. We know what to do with the SSM. We need to select software slave management because our software needs to control the CS pin. We need what to do for clock phase. We know what to do for clock polarity. We need to find out our data frame format. So let's look at this. So I'm trying to find out a bit of information, but you can generally see here. So we go 8 bits at a time. So you have 0 to 7 bits, and then you have that's 10 to 17 bits. And basically what I'm saying is we are reading this 8 bits at a time. So in multiple read-write commands, it's 8 clock periods. So 8 clock periods, what does it mean? It means that for we read 8 bits at a time. Okay. And both the read and write register commands are completed in 16 clock pulses or in multiples of 8. So our data frame format is 8-bit. So we know in SPI, we need to set our data frame format as 8 bits. The speed here, I've chosen the slowest speed, one of the slowest speeds, I think. I think there's only a 24 after this. No, actually, medium speed. I've chosen a medium speed for this SPI bus. The device mode is master because our microcontroller is going to be the master here, and we have a full duplex configuration. Cool. So let me look. Do we have any questions? No, no, at the moment. Cool. I don't know. Mm, 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 mm. I don't think I made it. Okay, cool. So no changes. So I don't know why that's claiming not to be saved. I must have changed some very tiny thing. But what am I demonstrating is that you need the datasheet to tell you how to set up the communication lines. Okay. And then once you know how to set up the communication lines, the datasheet does sort of tell you how an application is. No, no, no. The datasheet does sort of tell you how to operate this little device. However, I mean, it would be quite, so you would almost have to come to register mappings in order to, you'd have to come to register descriptions, and then you need to read all these register descriptions. And then as you read this description, so like right now, because I've already read and I know if I read the who am I register, this is kind of like a sanity check. So if we read this register, who am I, 0F, 0F, if we read this register, who am I, we should get 001111. So that's that's 00. So that's 03F. We should get this. This is a good this is a good register to start reading, because this register is unique to this device, and if we read it successfully, we know the data that we're going to read from this register is deterministic. We know what we need to get back. So if we do get the right data back, we know that our code is working and our driver is working. Cool. So sorry, it's cold, it's winter. Okay, cool. So this is how you would use the datasheet. So you'd have to go through all of this offset correction, offset correction. So what I'm going is I'm just reading everything. This is highly inefficient, obviously. But if this is the only option you would have, then you can use this. So if you just keep going through, we have VFC1, vector coefficient. I don't know how to use that yet. And this is going to be a natural state. You're going to be reading through the datasheet, not knowing how to use things. And that's why the datasheet is kind of difficult. You either want an application note or an application note with the most ideal thing, because then it would kind of tell you how to use both the datasheet and code to go at this. But if all you have is a datasheet and you go through it, you will find out, and it will take you some time. Okay, cool. So let's go. I'll jump now to a register I know, because I know we can use it and whatever. So if we go to control register 5 and we see, cool, this is actually a cool one. Output data rate. So we can select our output data rate. Cool. Block data update. Cool. Okay, cool. We can enable the z-axis, we can enable the y-axis, we can enable the x-axis. Okay, cool. So we can use this register, and you see it shows this got a little below, and we can see how to choose the output data rate for the device. So if you go through all the registers like this one, making notes, you will discover that you can actually find which register to touch first and how to touch that register. And once you touch that register, you can operate the device. And I know register 5 is also important. So this is anti-aliasing filter, full scale selection. Basically, this is our sensitivity. Are we plus minus 2G, plus minus 4G, plus minus 6G, 8G, 16G? We can enable a self-test. We can choose the serial Y interface, whether we're using 2, a 4, or 3. Okay, cool. So I know that's an interesting register. And I know if I go out X, so out X and out Y, so there's a L and a right, but I know this is the axis output for each axis. So out X, X, X axis, out Y, Y axis, out L, out Z, Z axis. And in some sort of piecemeal information, you can determine how to operate your sensor from the data sheet. However, there is another document that is very useful. It's either called a reference manual or, well, a reference manual would be better, because a reference manual kind of takes you through. So if you go through, say, your microcontroller's reference manual. So I'm going to open a reference manual, this one. And I'm going to open this. And this, I'm going to open, since we're working with SPI, I'll open serial peripheral interface. And this is for the STM32F407 that we're using. And what I want to show is that the reference manual is going to help you. It's going to have a functional description in which you can go and read how this specific peripheral works, and then you can operate it from there. And then comes a third document. A third document is an application note. So an application note is this sort of document. And I'll show you the I would want to show you the table of contents so that you can see, like, this is okay. Well, let's look at this table of contents on the side. So operating modes, cool. Oh, how does this thing operate? So cool. And then we have startup sequence. Ooh, that's cool. Reading acceleration data, understanding acceleration. This is kind of what we want, because from the other document we know kind of where everything is. Okay, so we know all this register descriptions, we know all of this registers and whatever, but we don't know which procedures. Do I need to read one before the other? Do I need to do this or that before that? Do I need to set my sensitivity before I read it? So, sort of details. And this will explain, and an application note will ideally explain to you how to start up the device, how to run the device, in case, so this one goes further, if we want to use interrupts and such, and which registers we want to deal with, um, in case we want to use the state machine feature, and so on and so forth. So this helps in structuring your code so that you can actually operate the device. Okay, cool. That's kind of all the documents that I'm going to use today, anyways. And I'm going to be jumping in between all of those documents to kind of um, pull out the information that we need. And then once we pull out the information that we need, we can implement that information in code. And once we implement that information in code, we can go ahead with it. Next point. So let's take this to the code, I think. No? I would want to take this to the code now. So let's go to code. Let's actually look at the startup sequence. So okay, run through this document as well. So operating modes, we know we can choose our data rate selection, okay, and then it tells us how much power we consume when we select data. And then we have power down mode. So when this is cool, when the device is in power down mode, almost all internal blocks are switched off to minimize power consumption. SPI and I2C are active to allow communication. Content is preserved, and output data registers are not updated. Basically, it's in standby mode. Okay, so this thing is in standby mode when it's in power down mode. Okay, so therefore keeping the last sample data in the memory before switching to power down mode. Okay, cool. In normal mode, data are generated at the selected output data rate through the ODR weights. Cool. So in normal mode, we set an output data rate. An output data rate could be any of this: 3 hertz, 6 hertz, 12 hertz, 25 hertz, 50 hertz, 100 hertz, 400 hertz, 800 hertz, 1600 hertz. Okay, cool. 1.6 kilohertz. So in normal mode, we've selected a data rate, and our accelerometer will sample our axis, multiple of axis at that data rate. So if you're 100 hertz, then 100 hertz means you're going to sample this axis, so the y axis, you're going to sample it 100 times every second. So what does sampling mean? Sampling means you're going to read it or check it or take samples from it, acquire samples from it. Tell me what you are now. Cool. Tell me what you are now. It's going to do that 100 times a second. So that's the 100 hertz. So, and you can see how this document is much better than the datasheet, because this document is almost steering us towards having a working device. So the other one told us how to communicate with the device. Cool. Now we have that set up and we kind of have a connection. So if we have SPI set up to this level, and we can initialize it, we basically have SPI enabled for that MEMS accelerometer. Cool. Cool. So this document, this application note is kind of pushing us down the road towards getting data from the sensor. Okay, cool. It explains the times. So when you're moving from power down to normal mode, how long does it take? And depending on what your output data rate is and what your analog filter is, these are the samples. These are the times that it will affect your data rate. This is how long it will take to change from normal mode. I mean, from normal mode to power down, and from power down to normal mode. No, from power down to normal mode. Cool. And from normal mode to power down should be some constant. Quick, we can find it if you want, but that's the kind of data you find out when you're doing power consumption. Savings. Cool. So startup sequence. Once the device is powered up, so once you enable, I mean your device, your board, your board is going to your board since the device is on your board, it's going to, once your board is powered up, it's going to power the device up. Okay, cool. So we know the device is already powered up. So once the device is powered up, it automatically downloads the calibration coefficients from the embedded flash, okay, to the internal registers, okay. When the boot procedure is completed, i.e. after approximately 5 milliseconds, the device automatically enters power down mode. This is something you need to note. So in the normal operation of things, assuming you plugged in your board more than 5 milliseconds ago and it powered up, and then now it's done powering up, what this document is telling us is that our device goes into power down mode. So the first instruction we send to it, we have to assume that the device is in power down mode, and then that is our determinate state that we will start from. And what does this document tell us to do? So this document tells us to turn on the device. To turn on the device and gather acceleration data, it is necessary to select one of the operating modes and enable at least one of the access to control register 4. So let's go back again. So you remember in our thing we had control register 4. We can look that, but we still have register description on the application note, so we don't have to go back to another document. We can just look at control register 4 and in depth and understand it. So this is control register 4 at address 0x20. Okay, so basically if we write to 0x20, which is an 8-bit number, so which is an 8-bit location. Now what number? It's a number anyways, but it's an 8-bit location. So you can see we have bit to enable access Z, Y, and X. Okay, and then we have a block data update. So let's quickly look at the block data update just to know what it does. If you're reading the angular data rate, if the reading of the angular data rate is particularly slow and cannot be synchronized, or it is not required with either X, Y, Z, and DA bit in the status register or the DR ready signal, it is strongly recommended to set the block data update bit in 1, and this avoids reading of values related to different samples. So we have a low and a high register. Basically what this does is make sure that when you read the low and high register, they are of the same sample. I don't know if that makes sense, because you get the data for one axis from 2 registers. Those 2 registers are updated independently of each other. Now have an extra feature here that ensures that when you do read one of the values, it is the one connected to the other value. So if you read a high, the low connect. When you next read the low, it will be the one connected to the high you read. Okay, cool. So that tells us what to do with that. So we know. So basically what it says here is we need to set which access we want, set our data rate, and decide whether we want block data update or not in order for us to get the device to turn on the device and gather acceleration data. We need to do those things. Cool. And if we do 67H, which is hex to binary, I think it's 67, convert. We have 0, so 0, 1, 1, 0, 0, 1, 1, 1. So what does this mean? Let's look at the table. Let's look at control register 4. It's telling us to write 67 hexadecimal to control register 4. What does that mean? We have 1111. So X, Y, and Z are enabled. Cool. X, Y, and Z are enabled. Cool. So that is 1111. Cool. And then 00, that's the next one. So what's that? What is that register? So X, Y, and Z are registered. BDU is O, so it's not a, it's disabled, default value. It's a disabled. And then we have this, the ODR 0 to ODR 3 is now 0. So ODR 0 to ODR 3 is 0, 1, 1, 0. Okay, cool. So what does that mean? 0, 1, 1, 0. So this is 0, 1, 1, 0, 0, 1, 1, 0. ODR 0, 1, 1, 0. ODR 0, 1, 1, 0. 0, 1, 1, 0. What does that mean? 0, 1, 1, 0 now. 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 0. Okay, there's a problem here, obviously, as I'm probably reading it wrong. So let's look at the data again, slowly. Cool. So that's 0. Okay, cool. 0, 1, 1, 0. Okay, cool. Let's look again. So 67H. So power down, 0, 0, 0. Cool. We don't want that. Oh, cool. I'm missing it because it's down here. 0, 1, 1, 0. Cool. So basically, what are we doing when we read this? When we have a startup sequence like this? So we have enabled X, Y, Z, and we've selected output data rate to 100 hertz. So selected. This is if we need an interrupt on P1. I'm not going to use interrupts today. I just want to read the data. Okay, cool. So I just want to read the data from one axis and have that data from that axis. If I have that, then we have that and we can basically build out our data processing further. But today it's just interfacing. Today, all we're doing is just interfacing with this sensor. So let's go start. I think we have enough information of how we want to start that we can start and kind of explore. Okay, cool. So the first thing I want to do is do something deterministic. Okay, so it's a very simple thing. I don't have to set up anything. I can just read this thing, and if I read this thing, I get this data. My drive is working. So I want to build up to read the device identification register. It's a read-only register. And if we get the right data from here, we know SPI is working, our device is working, and we can now go on with setting it up and running it. Cool. Let's do this. Okay, so go back to my code now. So I'm in main now, and basically my main, okay, cool. I include my SPI. Okay, cool. I define an SPI handle. SPI2 handle. I should actually just name this SPI1 handle. And then go down everywhere there's a problem. So I tested this with SPI2 because SPI1 is not working. And this is kind of the place where I went and I discovered that I need to, this is one, 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 this is one. This is one. Still something down there. This is one. Okay, cool. So let's look at this code from the top. We're going to add more, but for now we'll just look at it from the top. So we have a handle. We have an actual RX, which we'll use later. We have a dummy read, which could be a read right now. It's just fine. This is an experimental. It's just a byte that we are holding on to that is a different value and we can use. So let's initialize our SPI. So let's go to the definition of that. Initializing. I didn't want to do this code here because this is not the code for you. The code for today is to actually read the device, not to build up SPI. So SPI2 init, SPI1 init. God. SPI1 init. Okay, cool. So let's go here. So system booted with default clock. I'm not setting up any clock, so it's going to go to the 16 hertz clock, which is the ST standard. Then let's initialize SPI1. So let's go to definition and look at it. Alt function register. That's fine. That's for later. So let's look. What are we doing here? Okay, cool. So what are we doing here? We're setting up our MOSI pin. Cool. We need to set it to alt function 5, MISO pin, serial clock, and we're setting up our NSS, our chip select pin. So if you notice, these are all set up in normal SPI fashions. Okay, and then obviously we enable GPIO-A and GPIO-E. GPIO-A so that we can use PA 5, 6, and 7, and GPIO-E so that we can use PE3. Cool. So, and then we set up SPI there, SPI setup. Cool. And yeah, so these are all just debugging stuff, and we debug at SPI1. We are enabling SPI1 there, and we've enabled SPI1 once we set it up. Cool. So that's the first thing. Okay. This is just setting up. So I would run it. So let's run this by debugging. And my printf walks through, if you want to see the code, my printf walks through syscalls, and I have modified ITM centra so that write actually does ITM centra. Is right. I mean, pardon me, I have to move slowly. Attribute right, here it is. So basically what we have here is whenever we have printf, instead of it going to the IO, it goes to ITM. And what that means is if we open our ITM data console, so that would be in terminal, ITM port, and we go to our main where our code is stuck on the first printf, and we run that code, what that means is we get ITM debug data. Cool. So if we have this, we can now start working. Cool. So we know where we are. So let's initialize SPI. So what I want to do is I want to go to, I'll stop it. I'll stop it, and I want to run it so that it can give me that perspective it gives me on this side. Cool, perfect. So let's look at, let's run this. Okay. So before we do say SPI init, so let's look. Just to know that our code is working. So let's go and look at the RCC block, and I would look at APB2 ENR. I know all these things because I've been trying a lot. It's not natural to know. I'm just saying this so that people know when you're watching someone do something, it's probably because they practice stuff, and it's not because they already know everything. So SPI1 is not enabled. Cool, that's fine. And then if I look at, I think it's APB HB1. Is it APB1 or HB1? HB1. I think it's HB1 because GPIOs are on the fast bus. They're fast bus. They're really fast bus. GPIO A is off. GPIO E is off, and those are the ones we're gonna use. So if basically, if I initialize SPI right now, what should we have? We should ideally have SPI1 in RCC enabled, APB2ENR, APB2ENR. SPI1 should be enabled here. And then also our SPI peripheral itself. So let's come and find the SPI peripheral itself. Cool. Our SPI peripheral itself should, in our CR register, should have at least SPE enabled. We should have master should be set. This are still gonna stay low. This is going to be like something like a 111. Software slave management should be set. BFF should be unset because 0 is O. And then we should have a combination of these two just to have full duplex working. Yeah, so let's run that line of code, which is the code that we looked at below. Cool. So we're looking at GPIO 8 ODR. I think I'm looking at it just, I was looking at it just to make sure that what I'm wanting to know here is that GPIO E P3, GPIO E3 is 1, is high. What does that mean? Our SPI1 is deselected. So let's just go through the same register that we went through right now. APB2, I can see this brown means something changed. HB1 ENR, A was enabled, E was enabled. Perfect, cool. APB2 ENR. If we go through here, SPI1 was enabled. Perfect. So this is now, we are looking, we're seeing signs of our code working. Let's keep going lower. Let's go look at SPI1. Okay, SPI1. Master, yes. Our baud rate is set. Our SPI peripheral is enabled, SSI is enabled, SSM is enabled, which means we can control. And then I think SSOE should be enabled as well. Yeah, cool. So that means we have master output and we can control our SPI peripheral as we set it up. So SPI is working, cool. The next part I want us to check is probably GPIOE. This should, we should assert that P3 is on. Okay, ODR. What does that? ODR1, ODR2. So what does it? ODR3. Cool. Output data register 3. What is it? It's 1. What does that mean? Pin 3 is on, which means SPI1 is deselected. We're basically in this model, this just a moment. I need to find out the correct information so that we can. Yeah, I want. Look right now. Communication interfaces, SPI serial communication. Ha! PE3 is high. What does that mean here? CS is high. So CS being high means our device is not selected. Okay, cool. So our device is not selected at the moment. Cool. So now let's kind of walk through this code and see what it does and kind of understand it. So who am I address? The address of who am I is 0 cross 0f. So this is basically this address. Who am I? 0 cross 0f. Okay, cool. And because we want it to be because we want to read it, we want to make the first bit, the least significant bit 0 needs to be 1. Okay, so we OR it with this, and this gives us 8f. Okay, so who am I address should be 8f. Okay, cool. So and dummy right is just some data, and who am I data is just some data. So let's quickly run through this and see. We've initialized SPI. We are trying to read which address. This address X is going now to be the who am I address, which is the ORed address. So we have added the one, the one value so that we can make this address a reading address. Okay, and then who am I data is just a pointer to 0, and we want to know what is in there. Okay, cool. So let's run that right. Let's run those lines of code right now. Let's do the next printf. What is happening? We've initialized SPI1. We're reading from 0 cross 8f, so that is the OR of 0 cross 80 and 0 cross 0f. That's the address that we're reading, and the current value is 0. Cool. So drop P3 to select SPI1. Let's run that one. And that, what do we see here? Remember, I'm in GPIOE, ODR3 is 0. What does this mean? This means we've now transitioned from high to low, and SPI1 is selected. So that SPI clock is selected. Cool. So what do we want to do now? I want to send the address. Remember, the who am I address, the address I want to read. Okay. And I want to send one. I want to send this address and I want to read it. Cool. So enable SPI1 by making P3 low, GPIO EODR is this. So let's read this thing that it's now low here. So if we read it, it was 0 cross 8. So I think it's going to be 0 cross 0 now. Probably. Let's see. 0 cross 0. GPI EODR is 0. Okay, cool. So it's 0. It's nothing right now. So we've deselected. Okay. So now we are now going to send the address, who am I address of the location we want to read. Cool. So let's send that. Okay, so let's see. A few things have happened. We just sent that. We sent the data. We had an IRQ call. So we had a TX. We handled TX event. So remember when I was explaining this, our sends and our receives are non-blocking. So when we send data, we actually, what our sending of data means is we enable the interrupt, and then after we enable the interrupt, we write to the data register. And because the interrupt is enabled, it's waiting for something to be written to the data register. And the moment we write to the data register, it just sends out the data. Cool. So what has happened here? We have handled SPI TX event 1 IRQ called. Cool. So let's go back to main where we are. So now send data, now setting receive current value of dummy read. Now setting receive current value. Okay, cool. So we have sent that we want to read the address, this address. Now, the next thing I need to do is I want to tell the SPI peripheral, you're going to receive some data, receive it into this buffer. Which buffer are we using? Dummy read. Dummy read is currently 0 cross AA. So let's debug this and see what happens. Cool. So what has happened? We sent data. Now we've sent. Now we're going to send the receive, and the current value in receive is 0 cross AA. Okay. So this is just sanity checking. So I'm like, I have this data my dummy read into this dummy read and tell me what it is. Okay, so now I've already checked. It's 0 cross AA, so it's determined. It's what it was. Okay, cool. So let's read that. Already, so what has just happened? Look, we are receiving data. Yeah, we're receiving data. So we've sent a receive, and this receive is asking, basically, we're just being like, now pull back the data that we already had. Okay, so we've said now receive, and what we're receiving is FF, which does not seem right. So this is dummy read after RX complete. Okay, cool. So that's what let's keep going. Okay, so FF. Why is this FF? This should be 3F. I think it's because we did it too slowly and we missed some signals. Let's try again. Let's run it again. And now, once I just run it, I'll just run and we'll go to here and see. So what I want us to handle is FF. This is wrong because FF becomes what? FF becomes what? It's 1 1 1 1. So something is okay. I've done this code before. Disclaimer, and that's why it works. It should work. But I think I need to just look through my code again. Who am I address? We read that address. Just a moment. I think I'm doing my SPI has two functions. SPI has transmit. How do I explain this? There's something called SPI write read. You need to just let's put this there. Okay. Let's run this. Okay. I'm pretty positive I'm reading the data wrong somehow. Um, and I don't know why, because this should just work. So I'm getting the basically Giftive. I am getting the wrong data. Okay. I have a feeling nothing changed there, nothing changed there, nothing changed there. That doesn't change anything. Okay, cool. I have a feeling this is all because I've basically not um, I'm getting some corruption of data, and I wonder why. Just a moment. So let's go look at how I'm printing dummy read the first time. That's going to be our issue. How am I printing dummy read the first time I use it? Hash X, just hash X, just. Ah, perfect. Found it. Found it. Found my issue. Found my issue, and this is gonna fix everything that we're facing right now. So I need to do that. Okay, stop. So run. Start debugger. Okay, perfect. So let's go there, let's go there, let's do that, let's do that, let's do that, 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 do that. Let me read again. Cool. Mm. OXAA. Something's up. I am doing something wrong because I am getting OXFF and I should be getting OX3F. So I'm either reading the wrong location. Wait. Yeah. Um, hmm. Okay, just gonna do that also. No. Um, I have some sort of error in my code. I have some sort of error in my code, and I keep getting the wrong address. So I don't want to go on until I am getting the right address. And I have gotten the right address before. I just don't know what I made. Just a little confused with how done read. Okay, it's quite simple. I don't know how I managed to mess this up, but something is not working right. Hmm. I'm just removing a lot of my debugging steps right now to see if I can. Mm, this is quite painful because it was working just now. Do one more probe, do a send data, and then a send data and a dummy right again. Let's do that. Dummy right. Um, just a moment. I'm just gonna look at my old code from yesterday. Mm. So sorry. Where am I right now? Oh my word. So I think I have a solution. I think I'm gonna stop here today if this actually does work. So when we're reading into 16, when we're reading the ID, we need to run this into, we need to make this U in 16. I think this is going to work, and that's going to, I'm trying to convert it. I think this is the issue. So I need to convert U int 16 underscore t dummy read like that, and then I want to do, what is it, data. So this might fix it for us. This might actually be what we need. And in theory it should work, because if the thing is shifted 3 over, if the thing is shifted 1 over, hmm, if in theory this should work, because if I shift the thing 1 over, uh, I hate I hate it when I get to this point in my stream and then my code doesn't work. It's quite it's quite frustrating, but this is real. Um, no, that's the wrong one. 255 is FF and I want 3F. I'm handling my data wrong somewhere. Okay, so I have to debug this, and I wonder how I need to debug it. We are reading, SPI is set up, SPI is getting data, but for some reason, what, you, let's go to that. So this is wrong because this should be 3F and not FF. Setting that thing actually help. Maybe tying it all the way on. Stop. Just no, that's fine. Just run this thing. Let's see. Yeah. So something has changed since yesterday, and I need to go back and I need to revisit this until I make it work, and then I'll be back. Anyways, this gives us a chance to start tomorrow's stream at a point of not tomorrow's stream, the next stream, and this gives us a chance to start the next stream at a point of knowledge. Um, I'm quite confused as to why this was working and then suddenly just stopped working. I must have changed some very minute part of code that is affecting me now. And basically, we're just getting um, the wrong data. This should be 3F, and we're getting FF. Although we are reading the correct address. Mm-hmm. Hmm. Okay, cool. Thank you. Thank you for hanging out with me today. I'm going to have to stop that there. It was an incredibly awesome stream today. It was a good, like, kind of climbing through into what we are doing, how we're doing it, and where we're doing it. Basically, in summary, what did we do today? We set up SPI. We started speaking to the sensor, at which point the sensor is we are making a mistake somewhere, and our mistake is resulting in us getting um, the wrong data. So what I need to do is to go find out where the data is being messed up, and then after I find that out, I can basically come back and fix it. Um, it's not going to be too difficult. It should be quite straightforward. I'm probably just missing something somewhere. Okay, so that's gonna be it for today's um demo live coding session. Come back tomorrow and we can do this again, or someday. I might likely do it tomorrow. I'll see. I really want to do a lot more of this, and you can help me by getting me to do this um by getting me to do this. The way you can help me is by do just leave a comment, subscribe or like, and I can always um that encourages me a lot to do this sort of thing, and which in turn helps me to achieve what I'm trying to do. And I can make more of this. I can make more of these um, kind of. I can make more of these. The more why am I stuttering? I can make more of these with the more kind of like help you guys give me, and I really look forward to getting, yeah, us working together. Thank you so much, everyone, for today. I will try again soon. Cheers.